Next talk will be by Juan Fumero. I was thinking of how to squeeze in a one-sentence summary of his talk, but I realized that that is not possible, so I'm just going to let him start talking.
Okay, good. Thank you, Adam. So, hi, my name is Juan. I'm a postdoc at University of Manchester. Also, I'm an Intel innovator. And today I'm going to show you the project we're building for the couple of past 2 years with Intel. It's called Beehive SPIR-V Toolkit. It's in a sense, it's a toolkit meant to be used by a compiler, by that JIT compiler or static compiler. We use it in the context of JIT compilation for binary code generation, okay? For GPUs, FPGAs, etc. The thing about this library is that it's also automatically generated. You might wonder why you want to do this. Okay, stay to my talk. I will tell you why. So, I'm going to motivate why we do this, and then I'm going to show you a bit of background, okay, some terminology that I need. We are working in the context of Java, okay, automatical offloading code to run on GPUs, FPGAs, to accelerate workloads. So I need some, to set up some terminology. And then I'm going to explain to you the basic components or the main components of this toolkit. Later, what we did was to integrate this toolkit that you can have as a separate tool for your stuff. We integrated into the Tornado VM project. I will explain what it is if you haven't heard about that before. Okay, so let's get started. Why do we do this? So we initiated a collaboration with Intel, and the goal was to improve the Tornado VM ecosystem, the Tornado VM technology for the OneAPI software ecosystem. So OneAPI is a new toolkit from Intel that has many things, many libraries inside, and it has also new libraries for accessing accelerators. The thing about this OneAPI is that some of the libraries are accessible only through SPIR-V. SPIR-V is an intermediate representation, okay, standard portable representation in binary format to run on accelerators. So in Tornado, we need access to SPIR-V in binary format. So we thought, okay, this is complicated because it's not easy to generate. I mean, most of you have worked on compilers before. It's not easy to generate binary directly, right? So what we decided was to decouple the optimization process from the actual code gen. And the code gen is a standalone library, okay? And that's the part of the work that I'm going to present today. Right, so let's set up some terminology. OpenCL. OpenCL is called Open Computing Language. It's a standard, it's a programming model and standard for accessing accelerators, okay? FPGAs, RISC-V accelerators, AI, GPUs. Any vendor that implements the standard, okay, you can use that implementation to run your workloads. OpenCL has two parts. It's called the host code, it's the pure runtime. Let's say, allocate that buffer on the GPU. Run this kernel, that's the host code. And then it has another part, which is device code. The device code is the function that runs on the GPU, on the FPGA. And you can express with OpenCL that function in kind of C-like, okay? It's an extension of C. Or, recently, you can have a SPIR-V. SPIR-V is in binary. Obviously, you are not going to tell the developer the problem in binary. This is meant to be used by an optimizing compiler, okay? What's the benefit of SPIR-V? Well, one of the reasons is that many companies provide these kernels and they don't want others to see that code. You can disassembly, but it's hard to read that code. Another reason to have SPIR-V is that because it's very low level, compilation time goes down, okay? So we target SPIR-V. One more thing about this ecosystem. So we target also in the OneAPI ecosystem from Intel. OneAPI it's a bit confusing from Intel because they have the specification, which is open, and the tool or the implementation, which is also called OneAPI. Okay, but I'm referring here as a specification. It has many components, has a few compilers, libraries. You have libraries for deep learning, AI, acceleration of math operations, linear algebra, etc. What we are interested in is the low-level library. It's called Level 0. That's a quite close library to OpenCL, if you like. The thing is, to run Level 0 applications, you need SPIR-V. Okay? And that's what everything comes into place. Right, I hope that makes sense. And you can say, well, what's the deal? What's the gap here? Well, we have Tornado. Imagine you have a Java application that wants to use an accelerator through SPIR-V. Now, how do we currently access SPIR-V? Well, as it is right now, you can have your OpenCL program and then call an external tool like LLVM to go through, from OpenCL down to SPIR-V. So it's kind of weird, right? Because then we have to do a sub-process to call LLVM, it's totally decoupled, etc. No. Then another alternative is to have like a SQL program. SQL is another standard, well, many terminology here, but the key message is that this solution is based on C, C++, but we want Java or any other managed runtime programming language, okay? So what we want to achieve is the following. You have a Java workload, and you want to accelerate part of that Java workload on accelerators. Here is represented Intel HD graphics, Intel discrete GPUs, you can have NVIDIA GPUs, etc., etc., etc. So for the first part, we do this toolkit. So that's part of the talk that I'm going to show you today. So the toolkit is in these steps, in between the Java application and the actual code that we generate. And then for the whole view, we use the toolkit in order to go from Java down to the actual hardware. We execute the code, right? One thing is to be able to generate code, and then we have to execute the code. To execute, we need this low-level API called level 0. And I'm going to show you today these two tools. I'm going to focus mainly on the toolkit, but I'm going to show you how we perform with the LLVM at the end of the presentation. So let's talk about the toolkit. The toolkit has three components. It has the library generator, the actual library, and a client. Now, I'm going to go to the question. Remember that I said at the beginning, the actual toolkit is also generated. Why? Because what we did was, SPIR-V is a standard, okay? It's defined by Kronos. Kronos is a consortium of many companies, Google, Intel, NVIDIA, etc., etc. They agree on the specification for the intermediate representation, and they put a file in JSON format for the grammar. Today is SPIR-V 1.2. Tomorrow is 1.3. In next year will be 1.4. So what do? We take the JSON grammar file, we have our toolkit, to generate automatically a library. So for the next releases, hopefully, it's just a matter of milliseconds, right? Or a few seconds. Exactly, you got the point. So for the library toolkit, let's focus now step by step. So for the library, we use two open source software. We use, to parse the JSON file, we use an application, well, a framework called Jackson Annotation Library. And for the actual generation of the library, we use the Apache FreeMaker. So what's the goal? With one framework, what we did was to annotate, okay, based on the JSON structure file. And we get back the list of SPIR-V instructions, SPIR-V operands, and SPIR-V kinds, if you like, data types. So once we have those lists in memory, what we do is to use the FreeMaker library to, one by one, just generate Java code for those instructions and those operands. At the end of the process, you have a full library in a jar file format ready to be consumed by a customer, by a client. So just to give you a little bit more in detail, here I represent on the top left the high-level overview of that JSON format, okay? The JSON is divided for the SPIR-V specification. So we have two main components. The one that expands into more entries are in blue, while the gray ones are like a terminal operations, right? If you like. So the SPIR-V grammar is divided into two main blocks, instructions and operands, and then for each instruction we have a opcode, the capabilities of that instruction, and so on and so forth, and something similar for the operands and the kinds. So the first type is with the FreeMaker framework. We say, let's parse the whole grammar file, and then we say, okay, the file is dividing into the magic number, a list of instructions, and a list of operands, and whatever we can have in there. So once this is done, we have in these two arrays, SPIR-V instructions and the SPIR-V operands, all the instructions and operands that we have in the SPIR-V specification, all of it. And then we continue the process, and with the templates that we also have, you can think about the template like a Java-ish, okay, Java with a lot of, typical template programming. And then we fill those. So we have templates for instructions, and then we have templates for operands and kinds. At the end of the process, we have the whole library ready to be consumed. So let's talk about the library, how the library looks like, because we say it's functional and it's composable. Well, that's what I believe. The thing is, if you know what to generate, that's the key part. You have to know. But if you know what to generate, it's very easy to compose, to build SPIR-V module. So let's say SPIR-V module, the standard tells you, start with a header that has the magic number, a version, a bound, and a schema. So we say, in Java, because we do code generation from Java, okay, it's a Java library. We say, SPIR-V module, build the header with the major minor version, the loop bound, the ID bound, and the magic number. And that's on, okay? We continue generating in the library side with all these instructions, and when we close the module, it's already stored in binary, right? Let me give you another example. So the SPIR-V has capabilities. You can have, for example, if my module, my kernel on the GPU uses FP64, I have to enable as a capability. So it's as easy as I add in the module a new capability, and I add, for example, in this case it's in64, but you can have FP64. Or I add this module is going to be a kernel. Kernel means for compute, not for graphics. Okay, we're using, by the way, we're using the GPU for compute, for acceleration of workloads, not for graphics. SPIR-V is a common representation for both compute and graphics. While we focus on compute and we have the library open source, that means, and we cover the whole spec, that means that someone, if you want to, you can have Vulkan applications running with Java. That's very cool. We haven't explored that, so we focus on compute for now. Okay, just to give you a flavor of another example, more useful example, let's say we want to cover this structure if-else, okay, from the OpenCL side, how will look like when you program the library with the library. So you have an ID, SPIR-V is an SSA representation, and we use in our compiler Graal SSA, so it's a perfect match. So we say, give me a new ID, it's going to be for the comparison. Then I have to add an instruction called operation I equal, it's an integer it's an integer. Then we build the instruction, and then we build the branch. The thing is, you don't have to remember all of this. You go to the standard, and the order of the operands and the type of operands is exactly the same as the standard will tell you. Okay? And that's a good thing. That's what I'm saying, that if you know what to generate, it's easy to build it. In fact, the way we did it was to use LLVM underneath. Okay? We have our OpenCL. We know what to generate from OpenCL side. We make use of LLVM and say, this is structure that I want to achieve. Okay? This instruction, this instruction, this instruction. So we build our compilers with all these libraries. Right, and then we have the client application. So as I say, it's open source, you can download it, and as a standalone, you can disassembly SPIR-V binary. But nothing special about it. It's just, for us, it was an example of how to use it from the client side. Right, so how do we test this? So we integrate this into Tornado VM. What's Tornado VM? Tornado VM is a parallel programming model, okay, a parallel programming framework for offloading a subset of Java to run on accelerators, okay, GPUs, and etc. And for the SPIR-V part, we took the library, okay, as a code gen. Right, so Tornado VM, even though it has a VM in it, it's not a VM by itself, okay? So it needs an existing JDK. In fact, the reason why I call it VM is because it's a nested VM, okay? So you have your Java application, and Tornado VM is a kind of in between, right? We call it VM because Tornado manages memory, manages compilation for you, manages execution for you, etc., etc. But it doesn't run by its own. It runs with OpenJDK-based distributions. OpenJDK we can also run with Graal VM, Corretto, etc., etc. And we don't compete with Java. So the main goal of Tornado is to complement what Java cannot achieve by itself, okay? So we want to run on accelerators, but we don't want to access directly to accelerators. That's the key part. Right, so what we did was, okay, Tornado VM has a few backends already. We had one for OpenCL, one for CUDA, PTX, it's assembly code for CUDA, and then we add a new one for SPIR-V with this library I was talking about. So, yeah, let me jump to this one. So what we did was to have directly the full JIT process, the full JIT compilation pipeline, right? So to integrate this Java library, we also need the optimizer. And the optimizer is an extension of the Graal JIT compiler. We use Graal as a library, right? So we extend Graal with a lot of phases, new nodes in the IR to be able to generate GPU, FPGA code. So in Tornado, I'm not going to go into much detail, but essentially there are many compilation phases. We have what we call a common IR. It's already Tornado IR. You can think about Tornado IR like a superset of the Graal IR, okay? We have more information. For example, we know if a loop is parallel, we remove the loop, for loop, and we say this is a parallel loop with a range, for example, things like that. We know it's a reduction, so we know how to perform a reduction in parallel, things like that. Then that's what we call a common IR, and then we start specializing. So the IR will look different depending on the backend you choose. If you choose CUDA, it will look different. If you choose OpenCL, it will look different, and so on and so forth. And at the end of the process, at the end of the JIT process, the optimizer process, because we combine Graal optimization with Tornado optimizations. For example, we call the parse escape analysis, okay? That's Graal. And then we combine with, at the very low tier, we combine with FMA expressions, so fast multiply add operations that very fast on these devices, by the way. Right. Once the code is optimized, we introduce the library I was talking about for the pure code gen to generate SPIR-V binaries. Okay, so I'm not going to go into the details here. I'm going to jump directly into the evaluation. So what do we do here? First, we evaluate the code generation itself, okay? We have a set of benchmarks. Each block, let's say, is group represent a benchmark. And in that benchmark, there are two versions. One for OpenCL, the one we already had in OpenCL, in Tornado VM, and the new one, SPIR-V. And we have, for each bar, let's say, we're dividing into two. What we call the code generation is the black portion of it, and the driver compilation. The code gen is the actual build module with the library that I was talking about, the SPIR-V Toolkit. The yellow part, the driver compilation, is the JIT part. So SPIR-V and OpenCL, you can think about both of them intermediate code. Then you go to the driver, you send this to the driver, the GPU driver, and the driver will do the final compilation, okay? And that's the time that is represented in yellow here. So let's analyze the black portions. The black portions are and the Y scale, the Y axis represents pure runtime. So the lower, the better, okay? In nanoseconds. This is in nanoseconds. So as we can see, the code gen takes a bit of more time, okay, with SPIR-V compared to OpenCL. Why is this? Because we have to build a SPIR-V module with all these, objects and so on. So it's easier to understand and to reason about, but we have more pressure on the Java itself because we are allocating a lot of objects, etc., etc. Right. Then we go to the driver compilation. So once the SPIR-V module is generated, then we compile to get the final module. And we see that it's around 4 times faster, 3.9 times faster, that part of the compilation. That makes sense. That's what we wanted to get, right? And overall, if we speed up the compilation process by 2.7x, which is great. Okay, this is the benchmark for pure code gen. But what about end-to-end time? How have we improved something? Well, now my baseline is Tornado VM running on the same GPU. It's an Intel GPU, by the way, I didn't mention before. The baseline is the Tornado VM running all these applications on the Intel integrated graphics. And I'm showing here speed up, so the higher the better, okay? So, as we can see, in most cases, running on the same GPU, but going from different driver or from different implementation, in this case is SPIR-V, you can get extra performance. There are a couple of reasons for this. So first of all, the number of threads that are deployed on this hardware are quite likely different between the two implementations. So even though we are running on the same hardware, the number of threads we deploy is different. Why is this? Because in OpenCL, in the Tornado VM, we have an heuristic. The heuristic, we took it from the NVIDIA guidelines. And as you can see, it's an heuristic, okay? Actually, it's a very long subject of study in academia about how is the best number of threads to deploy, right? In level 0, we go through the level 0 heuristics. So the number of threads we deploy is different. What does it mean? Well, I can deploy 1,000 threads, but depending on your block, if you organize 32 by 32 or 64 by 64, you can get different performance. In some cases, we deploy the same number of threads, but the performance was different. That's the case of the blue filter, by the way. The blue filter was deployed exactly the same number of threads. Okay, that application is computational photography. It's a filter for you blur part of the image. And going through SPIR-V with level 0 can give you more than 2x performance on the same device compared to OpenCL. But in general, it should be roughly the same. And what we see that in the average time, SPIR-V is slightly faster, but kind of it's 2% faster than level 0. All right, so to conclude, I show you here, first part was a toolkit. The toolkit was automatically generated to adapt to new versions of the standard as we progress. And then we took that toolkit to integrate it into the Tornado VM project to be able to actually generate and optimize Java code to be able to run on SPIR-V devices. And the final key message is that we can speed up the overall process of execution, not just compilation, but execution by 50% in some cases. And with that, I conclude my presentation, and I'm happy to take questions. Thank you very much. Yeah.
On your runtime graph, I was very confused by the axis. So it's listed in nanoseconds, but then you have like 2 to the 8 nanosecond. So is your essentially compile time like 1/10 of a second?
Yeah. Oh well. Okay. That's taken from our profiling. Our profiler takes everything in nanoseconds, so I dump everything there. Yes.
Okay.
A few milliseconds. Yeah, I should put it in milliseconds. Yes. Sorry.
Okay.
Yeah. You're right. Yeah. Yeah, Tornado has a default profiler you can enable, and by default it's nanoseconds because it's a more reliable unit from the GPU profiler. We take that from the GPU driver directly, and this is nanoseconds. Yeah. More questions?
There was one benchmark that had a significant regression. Did you look into it? Do you have a sense of?
Yeah, the number. Yes, that's the case I was mentioned that the number of threads are mismatched. It doesn't. So okay, just to clarify, number of threads is the same. Okay, because number of threads matches input size usually on GPUs. Block of threads, how you organize those threads on the GPU is different. Let's say I run 1,024 threads by organizing 32 blocks of threads, or 64, or 128. That can, on GPUs, believe me, this is a difference, right, in performance, and that's one of those, yes. In fact, what we see in general, just to tell you, so we see that level 0 get a better estimation of the number of threads compared to our heuristic in OpenCL for integrated GPUs. We plug in for a proof of concept. Tornado can run also on the new ARC GPUs, the discrete GPUs. OpenCL is way better. Our heuristic is way better than the level 0 ones. Yeah.
So is this a situation where the main difference is not actually, is just the heuristic? Can you copy the heuristic?
Yeah.
Yes,
we try that. It's not that easy though. So, yes, it's easy, but we are not going to see the same performance because we are going through the level 0 stack, software stack with the driver, etc., and the OpenCL stack. Okay, so it's not exactly the same. So yeah.
Definitely time for one more question.
Hello, thanks for an interesting talk. I know for conventional CPU instruction sets, there are formal specification languages like SAIL. I don't know if you've seen SAIL for ARM CPUs. And I wondered whether the JSON file you take as input to describe your SPIR-V instructions and so on, whether that is kind of the basis of some kind of formal specification, and whether you're leveraging any of that infrastructure, you're just kind of parsing a text file and doing the stuff.
Yeah. Well, I don't know for the CPU, for the GPU. Well, I didn't go to the details. You can in the papers we have more details. So it's not just as straightforward as just parsing the JSON, putting the templates. We also introduce some utility methods for easy generation of code, like mainly factory methods, right? To be able to generate that code. So I don't think it's just as easy as taking that JSON and magically it's going to work. No. I'm not claiming that. Okay. But so what I claim is for similar programming models like OpenCL, for example, could work. Okay, in the same that SPIR-V can work here.
What gives you the confidence, Juan, that your code generator is correct?
Great question.
That's what I'm asking.
Great question. So, we have that in discussion in the paper. SPIR-V, the LLVM toolkit, has an SPIR-V validator, SPIR-V val, and we go through the SPIR-V validation. Okay, and everything is correct. If there is a minimal amount of something that is not correct, I'm not talking about the instruction in the wrong place. I'm talking the semantically not correct. It breaks. For us, the whole unit test suite plus the whole bench is passing completely with no errors. That gives us an extra confidence. Yes. Plus, we also have our own validator in the toolkit, and we discovered some like kind of cycle dependencies between instructions. We raise this exception, this issue to the standard. Basically, we check if the compatibility is correct. So I can't remember the details, but it was something like, if you want to use this SPIR-V capability, that works with compute and FP, whatever instruction. We discovered that we want to use one capability, and we say, but that's not valid in the SPIR-V format. But any driver was telling us that was raising the exception. Right? I raised this to the Intel community, to the Intel guys, and they say, okay, that looks like an error in the standard. I don't know if I didn't follow up, but yeah, we have an extra validation here. Yeah. Thanks.
Yes. Oops. I wanted to say if there's more questions, I'm sure Juan is going to be happy to answer them after the talk. I think